All right, guys, welcome to section 3.8. We're still working with our word problems, but in this section, we're going to be looking at exponential growth and decay problems. All right, and then just to do some quick examples of, or basic examples of these scenarios, we have exponential growth. Exponential growth in these situations, population growth, like with bacteria or like rabbits, since they normally double or triple or quadruple like every week or every month or every day. That's an exponential growth. So population growth tends to grow exponentially. Interest rates and compound interest rates, that also grows exponentially as well. And then we also have our exponential decay. Oh, it's a little too thick. That's okay. We'll go with it. Exponential decay. This is, radioactive situations where we have a substance that's unstable and it has a half-life, and every, few days or months or years, it decays by half. That's called the half-life, right? So substances, radioactive substances, unstable substances have exponential decay. Okay, so I say exponential growth. So remember your two exponential functions. Our first scenario for exponential functions is when our base is between or is greater than 1, and we have an exponential function that looks like that. Then our other scenario is when our base is between 0 and 1, and then our function looks like that. So these are the models that we're going to use for our growth and decay in this section, but this normally is going to start when time is equal to 0. So we're only going to be looking at these functions starting with t greater than or equal to 0. Okay, so there you go. Population growth, substance, exponential growth, exponential decay. So of course, since it's calculus, we're going to be concerned about the rate that things are growing. So we're going to be concerned with growth rates, how fast something is growing or decaying. So the rate of growth, what does that keyword sound like? When we're thinking rate of change, rate of growth, we're thinking derivative. Oops. We're thinking derivative. So how fast something's growing, right? For instance, let's think of like a population of bacteria. How fast it's growing is going to be dependent on the size of the population. It's going to be proportional to that population. So for instance, if there's one bacteria and it doubles every hour, well, it's going to go from 1 to 2. That's not that big of a growth rate. But let's say we have 200 bacteria and they are going to double in an hour. Now we're going to go from 200 to 400. So that's a much more dramatic growth rate. So when we're talking about exponential growth and decay, it's proportional to the size of the population. And the size of the population, it depends on where we're at on our exponential function. So it's proportional to the population, y equals f of t. Okay, so look at our growth rate is going to be proportional to the original function. So when we're saying proportional, normally that means we're multiplying it by some constant. We're going to call that constant k. Okay, so the rate of growth, f prime of t, is going to be equal to k times, we're going to say k times f of t, or k times y. All right, so when we're talking about, well, let me rewrite this. So when we're talking about exponential growth and decay, we have the law of natural growth. Natural growth is exponential growth. F prime of t is like dy dt is equal to k times y. And we know that there's only one function whose derivative is proportional to itself. And the only equation that satisfies that is our exponential function. So the only equation, and we saw that when we were developing E. All right, so the only thing that's going to satisfy that is y of t is equal to a constant, some constant, times e to the kt, okay, where k is that constant. We can take the derivative of that using the chain rule. All right, so again, we can just prove that y of t, taking the derivative with respect to t. Constant we can worry about at the end. The derivative of this, we can use the chain rule. Take the derivative of the outside function first, times the derivative of our inside function. Okay, I'm going to rearrange the terms a little bit. I'm going to flip those two constants. All right, and then this right here is exactly what y is. So we have that the derivative is equal to k times y, which is exactly what we have up here. Okay, so there you go. So this is how we're going to model our natural growth and decay functions. Okay, so let's talk about what that C means. C, notice that's what happens if we let time equal 0. So if we let time equal 0, we get k times 0 is 0. And what's e to the 0? It's just 1. So that constant C is, remember, y represents the population. I'll go back up to our growth functions and decay functions. Y represents the population at time t. So if y of 0 is c, if y of 0 is c, that means c is our initial value, or like our initial population, or our initial investment, something like that. So c is the initial value at time t equals 0. So what we normally see when we're working with our formula is that instead of c, we'll say that our exponential growth or decay function is equal to y of 0 times e to the kt. Just to emphasize that c is the initial value. All right. And then the only thing left we have is k. So let's explore what k means in our function. Okay, so exploring k, because now we know what c is. Let's explore k a little bit. And what we do know is that the derivative of y with respect to t is equal to k times y. That's one of the formulas we just derived. So solving this for k, because that's what we're exploring k, we can divide both sides by y. Okay. So we have that 1 over y times dy dt. Really what we did is we divided both sides by y. That's what this means. So let's write it like that. I think that's a better way of writing it. Divided by y. Okay, so what this is saying, let's break this expression down into just words. This is our growth rate with respect to t, right? dy dt is the growth rate. The derivative is the rate of growth. Derivatives are rates of change, so it's the growth rate. Divided by, and y, remember, is the population size. So this is what k is. That's what k is. So what that is saying, growth rate divided by population size, it's the relative growth rate. We call that the relative growth rate. And it is a constant. All right, so now that we have this formula, and we know where all the parts are, the c and the k, and why we're choosing exponential models, we're going to look at some examples. And we're going to start with section 3.8, number 4, and we're going to start that in part 2 of our video.